Alright, introduction to water treatment. General purpose scope water treatment projects. Two, water treatment process selection factors, preliminary treatment, aeration, coagulation, fluctuation, uh, sediment basins, filterization, disinfection, fluoride adjustment, taste, odor control, softening, iron, magnesium control, corrosion scale control. This course is adapted for the Unified Facility Criteria, United States government, which is public domain, is authorized, unlimited, distributed, is not copyrighted. Alright, general purpose and scope. This introduction water treatment system with the technology not designed with a manual, with the exhaustive treaties, with the intent for the engineers who are not regularly involved with water treatment projects, but who are interested in learning some of the basics involved with the criteria to be followed to determine the necessity for and extent of the treatment are discussed here, and our procedures are applicable to planning of water treatment projects. Water treatment projects. State Health Department, State Water Resources, U.S. Environmental Protection Agency personnel as appropriate should be consulted at the early stage of the project planning, regardless of supply source and associated water treatment needed. In addition with the usual treatment that may be required to ensure that the delivery of portable water conservation will given the need with the special treatment to the protect pipeline, water heaters, plumbing fixtures, and other equipment against scaling, corrosion, and staining. Because of the widely varying condition for the many types of the water, if it's not possible to establish criteria all came for the special water treatment. Treatment of the prevention of scaling and corrosion may not be entirely effective. In order to make the decision are as necessity for the special treatment cannot be reached prior to actual operating expense, but the general special treatment will provide only when the cases who are studied with the water analysis of the experience with the water definitely show that there were subtle corrosions of the water, severe corrosions of the water system, and or that severe scaling of hot water heaters, storage tanks, other parts of the plumbing system will occur. Marginal case for the deferred treatment provided only after operating experiences determines treatment to be necessary. 2. Water treatment process selection factors. The design of the treatment facilities will determine if the feasible study with the consider of the engineering, economical, energy, and environmental factors of all legitimate alternatives will be identified and evaluated by life cycle costs analysis, and additional energy used of the bed between Kennan's process will be considered for the purpose of the energy consumption, but the energy purchase of the procedure will be included with the use of the evaluation. All treatment process systems will be compared with a basic treatment process system, which is a treatment process system accomplishing the required treatment at lowest first cost. Pilot or laboratory analysis will be used in conjunction with the publish of the design data for the similar existing plans to ensure optimal treatment if it's responsibility for the designer to ensure the selected water treatment plant process comply with the federal environmental agency, state, or local regulations where stringent. Preliminary treatments of the waters contain fish and debris which can clog the damaged drains, pumps, damaged pumps, and clogged pipes cause problems with water treatment. Streams can contain high concentrations of super and suspended sediment. Preliminary treatment processes are employed to remove debris and part of the sediment load. Alright, screen. Core screens with the rack. Core screen with the often termed with the bar screens or racks must be provided with integral intercept large suspended floating material. The screens racked are made rakes are made with 1/2 3/4 inch metal bar with space provided with 1 to 3 inch openings. Alright, filling screen. Surface wire with the required screen with the train with the removal of the material too small with the intercept with the coarse coarse rake, and that must be basket type with the line strain with the manually hydraulically cleaned with the backwashing wire of the traveling type, which are cleaned by water jets. Fine screen clearing opening should be approximately 3/8 of an inch. Velocity of the water screen opening should be less than 2 feet per second at a maximum degree flow through the screen and the minimum screen submergence. Ice clogging. Northern area of the screen may be clogged with frazzle, anchor ice exposure for the rakes. Screens the cold area favors ice formation. Submerged parts should be avoided with the maximum participant practicable extent with the steam and electrical heating, diffusion, aeration, flow reversal have been used to overcome ice problems. Disposal of the screens. Project planning must include the provision of the disposal of the debris removed by the course of the fine screens. Flow measurement. Water treatment process. Chemical application were related to the rate of flow of the raw water, therefore is essential for the accurate flow rate with the measurement of the equipment to provide with the pressure differential procedure of the venturi type of the commonly used with the measurement of the flow and pressure continuities. Alternative selection of the pressure continuities of the magnetic flow of the meter. If the minimum velocity through the meter will be 5 feet per second or more, partial flume can be used for metering. Open channel flow signals from metering devices selected should be transmitted to treatment plant control center. Flow division. When a non-treatment process, flow division, flow splitting is an important treatment plant feature that must be considered in an earlier stage of the design to ensure that it can continue with the operating during major maintenance plants are frequently designed with a parallel identical chemical mixing sedimentation facilities. No rigid rules can be given to the extent of the duplication required because of the multiplicity of the factors and influence of the decision. Normal aerators are not provided with the duplicate sedimentation basins may not require duplication, and maintenance can be scheduled during the periods relatively low water low raw water sediment low fouling plants unit that can tolerate temporary sediment overload to determine the pre-sedimentation at all times essential for the reliable plant operation. Flow division should be made with the head of the pre-sedimentation basins by means of identical splitting weirs around so that the flow over the either weir may be stopped when necessary. During normal operation, the weirs will be accomplished a precise equal division of raw water regardless of flow rate to parallel subsequent units. Rapid mix, slow mix, sedimentation water that would then be combined and distributed into filters. Pre-sedimentation units are not provided with the flow with a commonly split head with rapid mixed units. Single treatment train is to provide with initial with the expectation of adding parallel units in the future. Then the flow splitting facility should be provided as part of the original design with the provision for the mock flow over the weir, which is to serve future units. Alright, sand traps are normally required with the surface of water treatment of the plant with the principal application for the removal of the fine sand from well water. The presence of sand in well water is usually a sign of the improper well constructed towards development. Sand pump that cannot stop the reworking the well with the sand must be removed, otherwise it will create serious problem with the distribution system by clogging severe surface pipe meters plumbing. Central figural sand separators are often effective, meaning that the sand removal with the cyclone separated size devices are available to assemble, but the manufacturer require no power are then supplied by the flowing of the water. The operator under the pressure, therefore, repumping is not necessary. Water from the well pipe enters tangentially into the upper section of the cone, and central figure forces move the sand particles to the wall of the cone. Then they pass down the water into the outlet chamber. Sands and periodically drain waste from this chamber through a valve that can be manually automatically operated, clarified with water discharge at the top of the cone. The units available, the diameters of 6, 12, 18, 24, and 30 inches, providing the capacity ranges from 15 to 4,500 gallons per minute, and are suitable to operations up to 150 pounds per square inch. Pressure drops through the unit ranges of 3 to 25 psi, depending on the unit size, flow rate. These separators will remove 99% of the plus of the 150 mesh sand, about 90% of the plus mesh, 200 mesh. The units are rubber line protection against sand erosion. Planned sedimentation, also known as pre-sedimentation, is accomplished without using co-gallagating chemicals, where the planned sedimentation is essential judgmental decision influenced by experience with the plants treating water. For the same source of water derived from lakes and impounding reservoirs rarely requires pre-sedimentation treatment. On the other hand, with the water obtained with notable sediment-laden stream, such as those found with the Midwest, required with the pre-sedimentation facilities with the removal of the gross sediment load prior to the additional treatment. Pre-sedimentation treatment should receive serious consideration for the water obtained with the rivers, whose turbidity value with a frequently excess of 1,000 units. Turbidity values over 10,000 units have been observed at times in some central U.S. rivers. Plain sedimentation basins. Plain sedimentation or pre-sedimentation basins may be square, circular, rectangular, or invariable, equipped with a sludge removal mechanism. Alright, design criteria. Detention time should be approximately 3 hours based with the depth that should be given an approximate range of 10-15 feet with the corresponding up to the flow rates with the 600-900 gallons per day per square foot with a detention per square period of 3 hours. Short circuiting can be minimized with a careful attention to the design of the inlet and outlet arrangements where loading rates should be cannot exceed approximately 20,000 gallons per day per foot. Where pre-sedimentation treatment is continuously required, the duplicate basins should be provided. Basin bypass overload should also be included. Aeration. The term aeration refers to the process in which water is brought into the contact with the air for the purpose of transferring with the volatile substance from to and from the water. These volatile substances include oxygen, carbon dioxide, hydrogen sulfide, methane, volatile organic compounds responsible for taste and odor. Aeration is frequently employed with the plants treating groundwater for iron and magnesium removal. Purpose of the aeration. The principal objective of the aeration are the addition of the oxygen of the groundwater of the oxygen for oxidization iron magnesium. Groundwaters are normally devoid of the dissolved oxygen added with the aeration oxidizes dissolved iron magnesium into soluble forms which can then be removed by sedimentation and filterization. Partial removal of carbon dioxide will reduce the cost of water softening by precipitation of the lime to increase the pH, reduction in the concentration, taste, odor producing substances such as hydrogen sulfide, volatile organic compounds, removal of the volatile organic compounds which are suspected carcinogens. Type of the aerator. The type of the aerators are commonly employed. They are either the waterfall aerators, exemplified with a spray nozzle cascade, multiple tray unit diffusion bubble aerators, which involve the passive bubble and compressed air through the wall of the mechanical aerators employing motor-driven impellers, along with a combination of the air injection device. The three type the water aerator employing multiple trays are most frequently used in water treatment. The efficiency of the multiple tray aerators can be increased by using enclosure blowers to provide counterflow ventilation. Design criteria: multi-tray tower aerators. Multi-tray aerators. Multi-tray aerators are constructed with a series of the tray with usually 3 to 9 with a perforated slot or the mesh bottom with the water first enter with a distributed tray, then fall with the tray to tray. Finally, entering collection basins at the base of the vertical opening between the trays, usually ranges from 12 to 30 inches. The good distribution of the water over the entire area of each tray is essential. Perforated distributors should be designed to provide a small amount of the head, approximately 2 inches on all holes, in order to ensure the uniform flow of the aerators and provide provision for the forced ventilation. The trays are usually filled with 2 to 6 inches media such as coke, stone, ceramic balls to improve the water distribution, gas transfer to take advantage of catalytical oxidization effect of the magnesium oxide depositing in the media. Water loading aerators should range from 10 to 20 gallons per minute per square foot. Good natural ventilation is a requirement. High efficiency multiple tray aerators design natural ventilation. The following empirical equation can be used to estimate carbon dioxide removal. Alright, your CR is equal to CO over 10 to km. CR is the magnesium, iron, carbon dioxide remaining. When ice problem with the aerator, the most housed in artificial ventilation by the end of the blower with the necessary with the include with the induced velocity for the draft of the aerator is required with approximately 3.5 to 6% cubic feet ventilation air per gallon water aerated. This enclosed aerator operating rate of 1.5 million gallons per day. Air requirements will range between 3,600 to 6,200 standard cubic feet air per minute. Part of the drafter aerators employ high air flows, exhibit a high efficiency for the additional removal of the dissolved gas oxidization of iron and magnesium sulfide power equipment to natural draft. Multiple tray aerators having the overall height of 10 feet with approximately 1.7 kilowatts per mgd. Aeration capacity, power demands, and forced draft units will be greater. Alright, countercurrent packed column aeration. Countercurrent parked column aerator tower, similar to the operation countercurrent multiple tray operators, are particularly efficient at removal of volatile organic compounds from the air stripping packed column. The aerators consist typically of the long thin tower filled with either a random dumped media, rashing rings, burrs, saddles, ball rings, or corrugated sheet media that held by the packaging support plate. Water is pumped on the top of the tower over the distribution plate with the fall through the media. The air is blown through the tower over the fan counter with the falling water. Pre-distributed plates are used throughout the column to prevent channeling of the water airstream. The efficiency of the tower is dependent on the extent of the contact between air and water. Detailed design can be found in various chemical engineering literatures, handbooks, AWWA, EPA publications. Diffusion aerators. Compressed air interjected with the water as flow through the rectangular basins. Variety of the air injector devices may be employed, including perforated pipe with a porous plate with the tubes of various patented Sparger devices. Basin size determined by desired condension time, with a commonly range of 10 to 30 minutes. The tank depth usually 10 to 15 feet. Air requirements supplied by compressor generally range from 0.1 to 0.2 standard cubic foot per gallon at water aerated. More advantage of the diffusion aeration system include particularly with no head loss free with the cold weather operating problems. Additional advantage of the diffusion aerator may be also used to provide chemical mixing power requirements are associated with the compression range from 1.0 to 2.0 kilowatts per MGD. Aerator capacity, aeration efficiency, terminal additional with the oxygen removal of the carbon dioxide, general similar, provide multiple type aerator areas employing multiple tray aerators employing natural ventilation. Alright, mechanical aerators. Mechanical aerators typically consist of the open input with the operating the water for the basin size to determine the detention time required. Basin depth can vary from 5 to 17 feet, with the average depth between beginning with the 10 feet. Major advantage of the mechanical aerators, particularly with the no head loss availability of providing mixing. Mechanical aerators are generally not as efficient with the aeration towers or diffuse aerators, and long detention times are required. Criteria installation aerators. Aerators a gas transfer process which is not needed in all water treatment plants. The decision whether to aerate or not require assessment of the economic water quality beneath benefits achieved by its use. Addition of oxygen. Aeration process of the commonly used with adding oxygen to groundwater is oxidizing iron, magnesium, hydrogen sulfide, and to the limited extent with the organic matter. Groundwaters are usually deficient with the oxygen. Aeration effective with the meaning of it as adding to it. Oxygen adding is normally required with the iron magnesium removal. The treatment objective of the aeration will also help the oxides, hydrogen sulfide, some organic matter. Part of the removal of the volatile substances, aeration, even the method of removing the volatile substance from the water. Groundwaters will be inhibited deficient of the oxygen can be ejectional level of the carbon dioxide. Efficient aerator will result near saturation of oxygen, about 90% of the reduction of the carbon dioxide content with the groundwater, lime soda, water softening plants, and carbon dioxide dissolved is water at the point of the application will consume lime without accompanying softening for high 500 milligram to liter of carbon dioxide concentration. Greater than 500 milligram a liter, the carbon dioxide concentration is encountered with the groundwater aeration removal will probably justified for concentrations on the order of 10 milligrams a liter or less. Aeration is probably not economically or valid. Before deciding aerator with the carbon dioxide removal, the cost of purchasing, maintaining, operating with the aerator should be compared with the value of the lime saved. As softening plants, each of the magnesium later carbon dioxide removal will affect the shaving of about 1.3 megagram of liter quick lime, or 95% of the calcium oxide, which is also reduced with the quantity of softening sludge produced proportionally. Reduction of hydrogen sulfide aeration is used with the removal of the hydrogen sulfide with oil water, the most efficient with itself with a hydrogen sulfide concentration not more than 1.0 to 2.0 milligrams a liter. Otherwise, may be used in conjunction with the chlorine dioxide with hydrogen sulfide not removed by aeration. Reduction of volatile organic compounds. Recent studies show that the aeration successfully employed to produce volatile organic compounds, total trioethyl methane, concentration chlorinated water to meet the USA EPA regulations with the trihalomethane concentration. Aeration diffuse of the multiple tray aggregators can be reduced. Total trihalomethane concentration at a low cost with the cost increase with the high concentration. Trihalomethane current counter pack tower aeration most efficient for achieving mass transfer of volatile organic compounds. Alright, your aeration summary. When icing proper, the aerator must be housed with the artificial ventilation fans and blowers necessarily enclosed with the induced with the positively drafted aerators requires approximately 3.5 to 6 standard cubic feet of ventilating air per gallon of water aerated. Thus, for an enclosed aerator operating rating of 1.5 milligram a day, air requirements ranges from 3,600 to 6,200 standard cubic feet of air per minute. Positive draft aerators employed with a high air flow rates exhibit the high efficiency with additional removal of dissolved gases, oxidization, iron, magnesium sulfide, countercurrent pack column aeration, particularly efficient for the removal of volatile organic compounds. Requirement of natural draft multi-tray aerators having overall height of 10 feet will approximately 1.7 kilowatts per milligram a day of MGD of aeration capacity. Power demands of low power force draft units will be greater in general. Aeration is worth of the conservation connection for the treatment of the groundwater supply with the conjunction with the lime softening with the removal of the volatile organic compounds. Surface water usually exhibits low concentration carbon dioxide, no hydrogen sulfide, fairly high dissolved oxygen. Consequent aeration not required for the removal of the addition of these gases. However, the surface water container higher level of the trihalomethane precursor of the groundwater. Therefore, need for the aeration may arise. Reduce the total trihalomethane following chlorination. Water high with a bromine containing trihalomethane are difficult to treat by aeration. Other methods of removal should be used in such coagulation and fluctuation of contact granular activated carbon. Colligation fluctuation. Colligation fluctuation properly defined as colligation mean with the reduction of the force of which time to keep the suspended the particles apart with the joined together with a small particle of the entire large settable filter particles as fluctuation flocculation. Thus colligation perceived the flocculation and the two processes must be considered with the conjunctive. The person for the colligation, flocculation, raw water supply with especially softer water supply with the often contained with the water range suspended manner, including suspended minerals, clay, silt, organic debris, microscopic organism ranging in size from 0.001,000 to 1.101 micrometer. Smaller particle size range are often referred to as colloidal particles. Large particles such as sand and silt readily settle out of the water during plain sedimentation, but the settle rate of the colloidal particles is low. That removal of the colloidal particles by plain sedimentation is not practical. Chemical colligation, flocculation process required that they aggregate the small particles from large particles which were readily sedimented with the base and settle in the sediment basins. Colligation flocculation process is established by stepwise and short time rapid mixing of dispersed chemical collagen, followed by a longer period of slow mixing flocculation to promote particular growth. Chemical colligant. Most frequently, the chemical colligant is against as aluminum sulfate. Aluminum colligant is also used in aluminum or filter aluminum. Dissociates water with aluminum sulfate, ion or sulfide oxygen 4, aluminum 3. Ions various aluminum hydroxide complexity with aluminum compound with collagens, potash, aluminum, sodium aluminite, principally the latter with the iron colligants include ferric sulfate, terrarious sulfite, ferric chloride, magnesium hydroxide is and also an effective colligant, organic polyelectrolyte compounds, applied low doses alone in combination with metal colligant, also implied polyelectrolytes are high molecular weight polymers associated with water to give large, highly charged ions. Polyelectrolytes associated with ion destabilize the colloids and promote their settling. The polymers can be classified anionic to cationic, non-ionic, according to the dissociated polymer. Ions being negatively charged, positively charged, or both negatively and positively charged. Collagen and removal of trihalomethane precursor. The recent U.S. EPA regulations limit the available of the trihalomethane. Total trihalomethane precursor concentrations finished potable water to help meet with the current maximum contaminant level of 0.1 milligrams a liter of the total trihalomethane trivalent metal ion colligant such as aluminum sulfide, ferrous sulfite, or various organic polyelectrolytes have been used to remove the trihalomethane precursors before chlorination. Naturally occurring trihalomethane precursors such as humic fulvaric compounds are only partially removed by the decolligation filtration. Colligation with aluminum or pH of between 5 and 6 optimum removal of the fulvic humic acid compounds. Ferrous sulfites exhibit the optimum pH, removing the organic compounds between 3 to 5. Fulvic acid requires twice the dosage of aluminum need for the humic acid for the additional anionic polymers dose of 1 to 10 milligram a liter. Also provides the same removal of the humic compounds. Efficiency of the removal depends on the type, concentration, organic compounds present in the water supply, pH, colligant, dose of the solid to liquid, separation, stem, optimum precursor for the removal can only be estimated using laboratory simulation techniques, such as simply jar testing followed by setting and removal of the precipitated colloids, membrane filters. Procedures can be provided with the information necessary to determine the optimum condition of the removal of dry halomethane precursors compound, monitoring the removal of the organic precursors, compounds, colligation, filterization, facilitated measurement of the total organic compound. Design criteria for mixing. Criteria: rapid, slow mixing process having the developed base for the detention time, power, input, velocity gradient, and the product, the velocity gradient detention. The value for the GI and GT are computed as, rapid mixing. The rapid mix for the detention period usually range from 10 to 30 seconds of itself with a mixture power approximately 0.25 to 10 horsepower per MGD. Power and detention time should be matched if the value for the G will be approximately ranging 500 to 1000 sec. To the negative first of the wire water efficiency with 80% of the water temperature 50 degrees Fahrenheit at a power input of 1.0 horsepower per MGD. Detention time 10 seconds. Seal to the G value with about 1000 seconds to the negative 1 and at the GT value 10,000. Similarly, 30 seconds detention time give the G value of about 600. GT value of the 18,000. Low detention period of the rapid mixing basin should be avoided because of the higher power requirements for the inferior colligation requirement. The rapid mixing basin should be designed to minimize short circuiting. Slow mix. The slow mixing follocating units detention period should range from between 30 to 60 minutes since isolate and solve with the mixture power approximately 0.1 to 3.5 horsepower per MGD. G valve the range from 20 seconds to the first or to 100 seconds to the negative 1 are commonly employed with the corresponding with G values, therefore range from 36,000 to 3,360,000. Tapered slow mixing with the G decrease to the maximum about 90 seconds to negative 1 down to the 50 seconds to negative 1 or 230 seconds to negative 1 can be used generally produced as such. Some improvement in flocculation. Some higher gauge G valve with a 200 seconds to negative 1 are employed in some water softening plants. Normal fluctuation aluminum iron salt with a maximum peripheral speed. Mixing units should not exceed 2.0 feet per second, and provision should be made. Speed variation control short circuiting in 2 or 3 compartments usually provided the computation can be achieved by using baffles. Turbulency following the flocculation must be avoided. Conduits carrying fluculated water sediment basins should be designed to provide velocity with not less than 0.5 feet per second, not more than 1.5 feet per second. Weirs produce considerable turbulence and should not be used immediately following flocculation. Sediment basins. Sediment basin flows of the fluctuation most common type of the sediment basin generally shown in figure 2.1 and 2.2. Recent innovation clarifies the helical flow of the speed of the contact reactor consistent and above the ground steel colonical basin. However, these above ground basins require a high head and additional pump may be required. Minimum of the 2 basins should be provided to allow one of the be outserved with the repair and maintenance of the design must include the arrangement of the permanent of the single basin when necessary. Design criteria. The sediment tank with the base for the criteria with the listed in the table 2.1. The sediment basin should have the adequate capacity to handle peak flow conditions to prevent excessive deteriorated effluent water qualities. The above design data represent the common condition of the higher overflow rates may be used with the line with softened planes with some of the plants employing the upflow clarification units as indicated with the table of the water treatment plan design with the ASE, AWWA, and CSSE. Unusual conditions may dictate deviation from the general criteria. Detention time ranging from 8 to 12 hours more provided. Civilization may be necessary for rectangular sediment basin shown here. This shows the circular sediment basin. Treating highly turbid waters, on the other hand, with a colonical clarifier with the most efficient softening and the turbide removal to require the detention time 1 hour or less. Design data should be examined in the laboratory and for the pilot plant, especially for a larger plant. Jar test, colligant, dissociation conjunction with a settling column and analysis to determine optimal design criteria with the beneficial for the design. If the space available to sedimentation basins is limited, multi-story basins in which the flow of the horizontal along one level then passes upward, then through the flows horizontally along another level may be utilized. A newer commercial development sedimentation with the tube settler may be with the capacity of the existing sedimentation basins must be increased with little space is available for the construction of the new sediment basin. The detailed information relative to the size of the capacity configuration tube settlers may be detained with the manufacturer's steel base, but the clinical clarifiers may also be with the expand the sedimentation plants. When space is available, limited to the clinical clarifiers stand with a pre-pedestal base, require less space with the conventional sedimentation basin. Sedimentation base inlets and outlet baffles must be carefully designed to minimize short circuit in the solid sludge, which settlements at the bottom of the basement must be removed before the depth of the sludge becomes great enough to interfere with effective sedimentation. General mechanical sludge removal equipment is a requirement. All basins must provide with a drain with the overflow basin covers usually forming a superstructure will be required in northern localities where ice is a problem. Table 2-1 shows the design criteria and sediment tank. The tank of the depth and 10 to 16 feet length, the width ratio 3 to 1 and 5 to 1, diameter 10 to 100, flow throw velocity 0.5 to 3 feet per minute, entrance velocity, inlet ports 0.5 to 2 feet per minute, detention time 2 to 4 hours, surface overflow rate 0.35 gallons per feet squared to 1.5 gallons per feet squared. Where overflow rate less than 2015. Flocculation sediment basins unit type of the usually circular but combined function of flocculation sediment and sludge removal. Flocculation is accomplished in circle center. Sediment occurs with the angular space between the flocculation section perimeter and effluent weir. Design criteria are generally similar to those applicable separate units. Or a suspended solid contact basin type of the combined with the rapid mixing flocculation sedimentation sludge removal with a single unit. The colligation flocculation takes place with the presence of the slurry of the previously formed precipitate with the sour cycled back with the mixing with the reacting zone. Upflow rates over the point of the slurry separation should not exceed 1 gallon per minute per square foot for units used as clarifiers following coagulation, approximately 1.5 to 1.75 gallons per minute per square foot for units used in conjunction with lime softening. Alright, filterization. Water is defined the separation colloidal with a larger particle capacity for the porous medium. The usual sand, granular color, granular activated carbon, suspended particles removed during filterization range. Diameter between 1,000 to 500 microns or larger. Several different types of the medium arrangement and rates flow with the filters can be used with the filterization process. Must be commonly used with the gravity filterization, but pressure filters, diatomite filters are used with smaller insulation. Recent high rate filters have been developed which require less space and have higher solid loading capacity with the conventional filters. Rapid sand filters, filterization rate. Rapid sand filters are those filters which commonly operate with rates between 2 gallon to 8 gallon per minute per square foot. Filter rate of filterization to be employed with a specific plan with be determined only after the careful consideration by the designer. Raw water quality probably efficiently pre-treatment that will consistently be provided. Good quality water is not assured with a low filterization rate. Adequate pre-treatment filter design will allow applicable rates up to 6 gallons per minute operating per square foot with little difference for the water quality emphasized with the high rates RTB with the design. Great care must be taken to ensure pre-filterization treatment processes include colligation, flocculation, and sedimentation will perform. Our satisfactory, consistently high rate of the operating definitely requires excellent pre-filterization treatment, especially for the case of surface water. Recommended that the data from the laboratory pilot studies utilized whenever possible rather than an arbitrary selection of criteria. Filter medium sand. Silica sand most commonly used with the filter medium. The depth should not be at least 24 inches or more, not more than 30 inches. While the sand is employed with effective size should range between 0.35 to 0.5 millimeters. Uniform consistency coefficient 1 to 3, 1.3 to 1.7. Filter sand use ranges size between 16 mesh US series sleeve to retain and 50 mesh US series sleeve. Approximately 100% by weight, the sand should pass 16 mesh and 90 to 100% retain 50 mesh on a 50-minute mesh sleeve. Filter sand should clean silica and sand have them exposed with gravity not less than 2.5. Hydrochloric acid volatility of the sand should be less than 5%. Anthracite. Anthracite is an alternative medium consisting of a hard anthracite with cold particle with the effective size commonly ranging from 0.45 millimeters to 0.6 millimeters with uniformly efficiency 19 is 1.7. The hard stage should not less than 2.7 on the MOH scale with a specific gravity not below 1.4. Also, the anthracite should be visibly free of clay and shale and dirt. Multimedia filters employ 2 or 3 layers of media different with a side with a specific gravity common arrangement. The dual media filter with a 20-inch of the anthracite overlaying sand layer with approximately 8 to 12 inches of the anthracite layer. The high size range of 0.8 to 2 millimeters. The sand layer with a 0.4 to 1 millimeter. Trimedia filters employ 18-inch anthracite layer, 8-inch sand layer, and underlying 4-inch layer garment illuminate having a size range 0.2 to 0.4 millimeters. Garnets have a specific gravity about 4, illuminate and about 4.5. Our filter gravel the under drain with a filter media with a commonly supported with an 10 and 8-inch layer with a coarse sand with a graded gravel. The gravel depth may range from 6 to 24 inches depending on the filter under drain system chosen. Gravel should consist of hard brown stones having a specific gravity of at least 2.5 and acid volume. Volatility less than 5%, 3 to 4 inch transition layer cores. Torpedo sand having the size range between 1.2 to 2.4 millimeters placed on the top filter gravel. Gravel size with a range of 0.1 inch to 2.5 inch filter under drain with the make construct with a perforated pipe grids. The various proprietary under drain system. Variety later are available. The design detail with the pipe under drain with given the numerous texts and handbooks manufacturers will furnish the design and installation criteria proprietary system. Sand anthracite gravel, the specification details, specification filter, sand anthracite gravel contained with the AWWA B100. Normal filters, no less than 2 filters should be installed regardless of the plane size. For large plane with a rough guidance for the number of the filters provided may be attained from N 2.7 to the cube 1.5, and the number of filter units is equal to 2.7 times the weight design capacity, the MGD. You obtain the 1 exponent 1/2. The 9 MGD plant would require 8 filters. So the filter unit, maximum filter size related with a wash water flow rate with a distribution. Normally, individual size does not exceed about 2,100 square feet, corresponding with the capacity of the 6 MGD. Flow rate is 2 gallons per minute per square foot. A unit size would require a maximum backwash rate of 60 MGDs a day. MGD. Which is excessive. Consequently, it should be divided into 2 parts equal side of the range of the separating backwash. 2 filter depth should be at least 9 feet. Filter backwash. Backwash facility should be capable of expanding filter media with 50% of the will require with a wash rate range of 10 to 20 gallons per square foot. Backwasher water can be supplied with a backwash pump from elevated storage provided specifically for the purpose. Filter downtime during wash period commonly average 10 to 20 minutes, including 5 to 15 minute wash period. 15-minute backwash single unit with the maximum rate wash water volume will be 300 gallons per square foot of filterization area. In that unit, addition backwashing auxiliary score is commonly provided. Aids in cleaning of the filter commonly accomplished by the rotary and fixed surface washer equipment located near the top of the bed. Is operated for a time period equal to that of the backwash. Water pressure 40 to 100 psi are required. For surface wash operation ratio of 1.5 gallons per minute per square foot. Air score must also be employed with not generally used an independent wash water storage tank is used. It must refill between washes. Typical capacity should be at least 1.5 times the volume of the required single wash. Wash water troughs equal the flow of the wash water through the provide continuity removal of the reused water. The 2 or more troughs are usually provided, but the evaluation of the trough bottom should be above with expanded bed with the clear horizontal distance between the troughs should not exceed 5 or 6 feet with the top of the troughs and not more than 30 inches above the top of the bed. Filtering and piping equipment. Essential filter controls are shown with schematically in Figure 2.3. Each filter should be equipped with a rate of flow controller plus associated equipment. Automatic filter water level control ladder sensitive of the water level. The main influent conduity transmits singular flow control. The controller will respond with a single adjusting filterization rate to match inflow from the sediment bag with the less of the practical limit of the total filter outflow with always equal to the total inflow filter water levels. Remain virtually constant with the device that will send with the maximum permissible clear water clear well level that should be also provided, but it should rain, but the maximum allowable clear well water level shut off. The signal will be transmitted to other file filter controllers. Also, audible alarm, other design not involved with the rate. Controllers such as influent, flow, splitting, and the variable decline rate have been developed, may be employed in discretion of the designer in general. Each filter must have 5 operating valves: influent, wash, water, drain, soft water, filter to waste. It's emphasized that the filter to waste piping must not be directly connected with the plant drain sewer. Efficient sampling tap must be provided with each filter. Valves can be manually, electrically, hydraulically, pneumatically operated butterfly type valve with the recommended with the filter service design philosophy commonly employed for major filters continues as follows. Our maximum water level, the water level that during backwash water level through the troughs, filter sand, filter gravel, water settling basins, water drain, filter to waste, filter drain, air gap drain, furated flow control, backwash water, filtered water to clear level, schematic rapid sand, filter operation controls, influent 1 to 4, influent 2, 3 to 6, wash water 5 to 10, drain 3 to 8, filter to waste 6 to 12, and that's feet per second. Efficient continuity must be trapped with the present back air over the provided with the shield of the rave of the control of the filter pipe. The gallery should have ample room, provide good drains, ventilation, lighting, humidification equipment for the gallery should be received. Careful of sterilization, filterization covered and by substitute strictly except under the favorable climatic conditions. Drainage from the operating floor of the filter should be provided with the curb access of the entire bed with the provided with the walkway operating floor level around the filter. Filters manually automatically controlled with local remote location. Facilities permitting local manual control are recommended irrespective of the other control features. Used backwash water should be discharged with a wastewater recovery basin waste to disposal facility. Regulatory agencies' general view of the view filter wash water with the pollutant forbid it to direct discharge to the natural drainage. Alright, essential instruments. Minimum essential instruments for each filter will provide flow rates, rate of flow indicator, loss of head indicator, effluent turbidity indicator, wash water radio flow indicating totalizing meter, wash water storage tanks provided with must be equipped with water level indicator while not absolutely required turbidity indicator with the main filter and influent but it isn't desired. Alright, diatomial filters. Filters accomplished with a little layered diatomaceous earth that support with the filter is tempered as septum. This layer of the diatomaceous earth is about 1/8 of an inch thick, depending with the filterization must maintain the filterization consistent. Feeding of the diatomaceous earth bed body fed with the influent water at the conclusion of the filter run layers of the diatomaceous earth will have increased the thickness about 1/2 inch. Filterization rates generally range between 1.5 to 2 gallons per minute square foot. Principal use of the diamite filters have been swimming pool water. Some of them installed treatment of potable water. Alright, pressure filters. Pressure filters, some of the construction operating character of the rapid sand filters have with the pressure filter medium gravel beds, under drains are enclosed in a steel shell with a very low net. New pressure filters in use today are the most common of these. Conventional downflow filter, high rate downflow filter, upflow filter. Advantage of the pressure filter is any of the pressure water lines leading to the filter not lost any of the case of gravity filters, but can be used with the distribution filter of effluent between 3 and 10 feet of the pressure head for loss. Through the filter. Primary discharge of the pressure filter is due to that of the filter being clothed in a steel shell. Access of the filter bed, normal observation maintenance is restricted. Also, steel shells require careful periodic maintenance, prevent both internal and external corrosion. The use of the pressure filters is not advantageous to most systems with pressure requirements and condition. Particular systems such as the pre-pumped filtered water can be limited. Cost saving will be realized. Conventional downflow filters. Conventional downflow pressure filters consist of the bed of granular bed multimedia with a good remove of the suspended solids compromise of the flue. The advantage of the gravity flow filters should include the lower installation cost, availability of wide differentiating piping system, hydraulic loads ranging from 1 to 4 gallons per square feet. High rate low filters. High rate downflow filter filterization rate 10 to 20 gallons per minute square foot. High downflow velocities require coarser media, which will allow the suspended solids to penetrate deeper into the medium and resolve. The more solids can be stored in the filter bed between backwashing is required. Many uses exhibit the 1 to 4 pounds square foot solids loading capacity filter. High filterization rates, also smaller, fewer filters. Use the conventional filters, however, the high solids loading capacity of the filter require higher backwashing flow rates, hence larger backwashing water storage tanks. Upflow filters, upflow multimedia filters allow filterization of high solid loads with a liquids concentration up to 100 milligrams a liter. 1,000 milligrams a liter. Advantage upflow multimeter filters is the coarse material and collections with the heavy particles with finer material collects the smaller particles. Efficiency and filter is increased. Alright, your upflow continuous backwash sand filters. Upflow continuous backwash sand filters continuously clean the filter remedial media by recycling sand internally through an air lift pipe, and sand wash. Regenerated sand is redistributed to the top of the sand bed. Once the sand migrates down to the bottom of the bed, it is again air lifted and represented the repeat cycle. Upflow continuous backwash sand filters require no backwash valve, storage tanks, backwash pumps, therefore its operation greatly simplified. R27 disinfection. I'm gonna cut the tape there. Testing.